I think we can start if you.
Okay, I'm ready.
Okay, welcome everyone, and thank you, Professor, for accepting our invitation. We are very excited to have your talk, and without further ado, the stage is yours.
Thank you. So today I'd like to tell you a little bit about what insights we can gain from the cognitive sciences into fast and flexible learning. So I'm not an artificial intelligence researcher. I study human cognition, but from a computational perspective, and I try to understand what makes us uniquely flexible at learning. So we're faced with new situations all the time, and we need to adapt to them flexibly. So, for example, we might get a brand new device that we've never seen before, and we're able to just very quickly figure out exactly how it works by generalizing our past knowledge from it. Um, Intelligent behavior necessitates fast and flexible learning, and humans are the unique benchmark for that. Um, and so what we try to do in my lab is to figure out what the processes are that support that. Um, and some of those processes may appear as less than optimal sometimes, and we try to understand why we have them and how they support them. So, for example, habits seem very inflexible and a little bit dumb, maybe, but having habits allows us to use our resources for something else. So, for example, you're so used to brushing your teeth that you can read a complicated piece of news at the same time as brushing your teeth. And when we try to study those processes in humans, we try um, to identify those extra processes by seeing what their idiosyncrasies are. So, for example, with habits, we can just um, do them without thinking about them, which means that they lead also to behaviors that seem sometimes buggy. So, for example, we might, be so used to waking up at a very specific time in the morning that we keep waking up at that time, even when it's vacation, and would rather sleep in longer. So I hope to convince you today that by studying humans, we can learn something about robots and artificial intelligence more generally. And of course, this goes both ways. So we take some algorithms from artificial intelligence to study humans, and then we try to fit this back this way. So today, more specifically, I'll try to ask what are the computations that support human intelligence, and whether those are just bugs of evolution or whether we should really think about those as features that are really important for having efficient algorithms. So I'll have two parts in my talk. In the first part, I'll give you some examples of the type of work we do to try to deconstruct the processes that underlie human behavior. And in the second part, I'll try to step away a little bit and try to think about how we can consider whether those are bugs or features. And by the way, I'm very happy to take questions at any time. And I can't see or either the chat or whether someone is asking a question. So if you have a question, please speak out so that I can hear it. Okay, so you know reinforcement learning, and I study reinforcement learning from the human perspective, so I still want to get on the same page about the type of language we use. So in reinforcement learning, we typically assume that an agent is in a given state and has the ability to act on that state, so to make choices. And those choices may lead to a different state, but importantly, they also lead to a reward, and this reward modifies how our policy, how we make choices in a different state. And here I'm just drawing a black box for the reinforcement learning algorithm that we use. Of course, there's a huge family of algorithms, and when we think about humans, we typically keep with fairly simple ones. So that's the framework. When we study reinforcement learning in humans, we typically use very simple games where participants are in a state and make choices and get rewards. Um, and where we try to understand how, where we try to set up those games so that we can test specific predictions about different algorithms. Okay, so it might look like this. So you're going to imagine you're a participant, you're playing a game, and you'll see a stimulus on the screen. In this case, the stimulus is an apple, and you get to make a choice. And in this case, the choice is just pressing one of three buttons, for example, computer keys. And at first, it's random. So this is a multi-arm bandit kind of setup. So you might try to pick the third action for the apple, and you might get 0 points, which tells you that this wasn't the right choice to make for the stimulus, and which tells you that you should maybe pick one of the other two next time. So maybe you will pick the left one this time and get rewarded, and be more likely to select the left one next time you see an apple. I hope that makes sense. If it doesn't, please feel free to ask questions. Experiments, typically we make them slightly harder than this. So, for example, you might have to learn not just to pick the left action for the apple, but you might also see other stimuli, for example, a banana, and maybe the left button is not going to be rewarding for the banana. So you need to figure out another one. Okay, so in this case, the framework of reinforcement learning that we talked about applies. You can think of the state as being the stimuli you see. So, for example, the apple or the banana. You can think of the choices as picking left or picking right or picking the middle button. And you can think of the rewards as the points that the participants get. And for the black box RL algorithm here, you can, we typically, when we do this type of experiment, we typically start from super simple RL algorithms that do the job just fine. Like this delta rule learning, that's a simpler version of the Q-learning algorithm, where we try to estimate the value of a state in an action simply by incrementing them with a reward prediction error. And because this is a contextual, multi-embedded setup, the choice doesn't impact the next state, so we don't need the temporal difference error here. Okay, so this type of algorithms have been super popular in cognitive science, and because they work really well at capturing how humans learn. And they're great, of course, because they're good algorithm. They're going to lead to having a good estimate of the state action value, and to a good policy. They capture human learning well, so that's a good algorithmic level description of human behavior. And something that you may not be aware if you're more on the AI side of reinforcement learning is that this algorithm is also really good because it has some biological plausibility. So we have this understanding of a network in the brain that goes from the cortex, premotor cortex here, to areas inside the brain, which are called the basal ganglia, that essentially implement this equation. So dopamine, DA here, is known to encode reward prediction errors, those terms, and it's known to send this information to the basal ganglia, which then use it to strengthen associations between state and associations. So really doing something that looks like a reinforcement learning. So for that reason, reinforcement learning has been very popular in cognitive science, cognitive neuroscience. But there's also been a strong understanding that it's really actually not sufficient to explain how humans are so flexible at learning. And in the next few slides, I'll try to give you an intuition for why that is, by showing you that even when you do a very simple choice, for example, picking between two items, like an apple or a banana, you don't just engage in reinforcement learning. You do engage in something that's like reinforcement learning. So if you're thinking of this child making this choice, they might have built this cached value or cached policy that typically they think apples are good, and typically they think apples are bananas are so they don't like bananas as much as apples, just by having experienced them a bunch of times in the past, and that might lead to a choice. And that's very much like what we think about value-based reinforcement learning. But when we make those choices, we rely on other processes. So, for example, you might have um, just smelled the apples and bananas and noticed that the banana is all black and that the apple smells really good. And so you might just be using your short-term memory to guide your decision right now. And that would be a very different process from using all your past experience to make this decision. Or you might also just remember past experiences in which you've had delicious apples and use this very long ago past experience to guide your decision. And then you would be using yet another process that is called episodic memory. Or you might just be picking the apple completely by habit, not paying attention at all to its value or not. You just typically pick the apple or you pick it. Or you might actually typically prefer bananas but might want to give apples a chance this time, and that would be exploration. Or you might use strategies. For example, if you know that apples from one store are good and bananas from another store are good, and you happen to know which store we went to, you might use that information. So even this super simple decision is actually supported by more than one process. And those processes are redundant, but also different. They favor different aspects of information processing trade-offs. But they're all playing a role at the same time when we're making even super simple decisions. So, of course, when we're learning, it's also very likely that more than one process is learning and supporting flexible behavior. And so that's why I try to understand in the context of reinforcement learning. So if we're doing this type of learning experiments, multi-arm bandit experiments that I mentioned before, I try to understand what the processes are that support them beyond reinforcement learning. So here's an experiment. So it's the same experiment I showed you before. We have participants see a stimulus. Here, this time it's a bicycle. We make them make a choice between three buttons. And they have to guess at the beginning, but then they have to use feedback to learn which action will give them what. So for example, here action 1 was correct for the bicycle, action 3 was incorrect for the car. They repeat action 1 because they've figured out that that was correct, and they'll need to figure out which action is correct for the car. This is a super simple experiment in the sense that the statistics of it are also very simple. So there's a single correct action for each stimulus, and there's no probabilities involved. So if you pick action 1 for the bicycle, you will always get a correct feedback. It will never change, and there will not be any noise in the feedback. So if you have perfect memory, it's very easy to learn. You're going to try all three actions and then know which one is correct and just stick with it. The key manipulation we do in this experiment is to have multiple independent blocks. So in block 1, you'll learn about the bicycle and the boat and the car, for example. But in block 2, you'll learn about a brand new set of images. Here, those are tools. And in block 3, it might be the fruit, and etc. etc. And so you have new little problems to learn at each time. And what we manipulate in this experiment is how many stimulus action associations you need to learn. So the set size here. The set size here is 3. Here it's 5. There's 5 stimulus action associations to be learned. Here there's 2 stimulus associations to be learned. And the reason we do that is that it's going to give us a way to show the limitations of reinforcement learning. Okay, so if we take our basic usual reinforcement learning algorithm that updates the value of the state and the action with the reward prediction error, it's going to build the policy. It's going to track the values as a function of the number of rewards you've obtained for a given stimulus. So we should be able to see that in the behavior. And that's going to be the only factor that matters. In particular, this reinforcement learning model predicts that the likelihood of making a correct choice depends on how many previous rewards you've obtained for this stimulus and on nothing else. So we can plot the simulations and the prediction. So we can plot the learning curves here, the probability of a correct choice as a function of the iteration number, which is how many times you've encountered the bicycle or the car or the boat. And this model just predicts no difference between the different set sizes. So it predicts that you should learn as efficiently for 2 versus 3 versus 4 versus 5 versus 6 stimuli. Again, I'm very happy to take questions if there's any questions for clarification, either on the task or anything. Okay, I can't see, so I'll just assume I can keep going. So this is a terrible prediction, and this is what participants do instead. So this is 78 human adult participants, but we've since tested it in many other populations. What you see here is that when participants learn about 2 stimuli, they look optimal, essentially. So if you take this dark blue curve here, the participants are changed in the first iteration, and then by the third iteration of the stimulus, they're very close to asymptotic behavior, and that's logical because essentially they've tried action 1, action 2, action 3, and now they know which one is correct, and they can remember that explicitly, and they can just stick with this correct action. Okay. But the more stimuli participants have to learn in parallel, the more incremental the learning curves get. So people do get good at the end, even when learning 6 stimuli, but they take many more iterations to get there. Okay, and this is not something that the reinforcement learning family of models on its own can predict. You can add various aspects to the reinforcement learning algorithms to make it have a little bit of a set size effect, but typically it doesn't get anywhere close to what participants are doing. So what we want to try to capture instead is this effect of set size, which looks something like this, where the probability of being correct is kind of optimal up to a threshold and then decreases. And something I'm not visualizing here also, but another aspect that we see here is that if you see the bicycle twice in a row, then you're much more likely to be correct at it than if there are lots of different stimuli in between. So the number of intervening trials also negatively affects the likelihood of a correct choice. So we can model this, and this looks exactly like what we think about as working memory. So working memory is this active form of memory that we use to remember information for a short time, typically things like a phone number or a password or something like that we want to hold in mind just the time to use it and then be done with it. We have a very limited capacity. People estimate it at 3 or 4 chunks of information, and it's very effortful to use working memory. And so this effect we see in participants looks like participants using working memory. So we can model this load effect up to a capacity and this short-term delay effect. We can just put this into equations by saying we're going to assume that we have a process that is going to store information perfectly for the last trial. So in this case, that means just storing the stimulus action reward contingency perfectly. But it's also going to forget very quickly. And in this case, it just means decaying towards original weights with a parameter. And then we're going to assume that we can only use this perfect memory in proportion to the likelihood of having stored this information in the capacity, which is going to look exactly like this curve here. Okay, so we're going to assume that a behavior is a mixture of those 2 processes, a mixture of a standard reinforcement learning process and this working memory process with a mixture controlled by the capacity. And when we do that, we can try to make different predictions from the pure reinforcement learning model. And we do capture human behavior much, much, much better than with pure RL. As you see, we can get this effect of very fast learning for low stimuli, but much more gradual learning for high number of stimuli. Okay, so the conclusion so far is that we actually can't capture human reinforcement learning with only reinforcement learning algorithms. We have to augment it with other processes that look like working memory to support this super fast human flexible learning. I want to just go a little bit further there to show that actually even the RL side here is not as clear as we thought it was for a long time. So to do that, we try to think about what really characterizes reinforcement learning in this task and as an algorithm. And something that characterizes RL is that in this case, it should be tracking value. It should be tracking the value of different choices. It should be able to react to outcomes, both positive and negative. So in this case, outcomes are very simple. They're either correct or incorrect, so either 1 or 0 points. And if it's incorrect, it's just an error. Okay, and so something that the RL algorithm predicts is how we manage error. So imagine you're learning about this blue stimulus here, and this is the correct choice to be made. So you should pick, you should press the left key for the blue stimulus. Okay, so each time you press the left key, you're going to get reward 1. And for example, let's imagine that this participant pressed the left key 3 times and each time got reward 1. Okay. Now there are 2 possible errors you could make. You could make the middle error, or you could make the error on the right. And each time you're going to get reward 0 for making those errors. And let's imagine this participant made the middle error twice and the right error once. So any reinforcement learning algorithm says that you should be penalized more for this one than for this one, right? You've experienced that it's bad twice, so your policy should have learned to avoid this error more than this error. Okay, so we're predicting with reinforcement learning that participants should be more likely to make this error than this one if they're going to be making an error at all. Okay, so what we're going to do is we're going to analyze participants' errors, and from their errors, we're going to analyze if they're more likely to make errors that they've made more often or less often in the past. So we're just going to count how many times they made the same error versus how many times they made the different error when they're making an error. Okay. And what we observe in the low set sizes, and set size 2 and 3, for example, is what we should see, which is that participants are more likely to make errors that they've made less often. So the number of times they've made the error that they're making currently is lower than the errors the other potential error. So that's as expected. But in high set sizes, we see that this difference completely disappears in high set sizes. So participants have a good avoidance of past errors in low set sizes, but the sensitivity to the negative feedback disappears in high set sizes. And we can check what our previous algorithm, the working memory and reinforcement learning algorithm, does in this situation. And it doesn't do that at all. You can see that in low set sizes, it has this characteristic pattern of avoiding errors well, but that pattern stays in high set sizes in a way that absolutely does not match what human participants are doing. Okay, so we're really showing that this prediction is failing here, and so that this model is actually not a good model of what humans are doing. And we think that's the RL side of the model that's having an issue, because in low set sizes where working memory is mostly contributing to learning, we're capturing behavior well. Okay, so we think that we need to go back to a model that had working memory and RL and change the RL part of things. And we need to change it so that participants are actually more likely to repeat errors that they've made more often in the past, right? Because that needs to counteract what working memory is doing to avoid past errors. So we are using something that's known in the literature, is that people don't just also have a tendency to just repeat what they've done in the past, irrespective of their outcomes. And that's called habit. And an equivalent concept in AI is value-free learning. So the idea here is that this equation we had before is going to say, well, you're more likely to repeat, not to be correct, to repeat a choice the more times you've repeated it in the past. And a simple way to implement this in an equation is to do something that looks exactly like RL, but instead of having a reward prediction error here, has just a choice prediction error. So if you chose something, you're just going to increase the weight of association between the stimulus and action, completely independent of outcomes. Okay, so we don't have RL anymore. We have working memory, we have habit, and when we take this model, it works really well. Actually, it captures the learning curves really well, and it captures also the error pattern really well. You see that this mixture model now is able to capture humans' lack of sensitivity to their past errors in high set sizes. And the plot on the right shows that this difference between the blue and the purple line here in late trials even becomes negative. So that means that the purple line goes over the blue line. People are more likely to choose something that they've made more of. And we can make the quantitative checks to verify that this model indeed does fit quantitatively better than other models. Okay, so we started from a behavior of humans trying to capture their learning from rewards. And we, in the past, people tended to call all of this reinforcement learning. So human learning from reward. Reinforcement learning was captured by a process that was called reinforcement learning that we assume mapped onto this very specific brain network that implements reinforcement learning. What we try to do is to show that actually it's much more complex than that. So we have this behavior of reinforcement learning in humans that is captured by a mixture of multiple algorithms, including working memory and this habit algorithm, and potentially also RL, although we don't see it in this specific experiment, but it's possible that it's still there. And those are supported by many different brain networks, and it's not completely clear exactly how those map onto each other. And that's part of the work we're trying to do, is to figure out where that goes. Okay, so it's more complicated than we thought. Reinforcement learning in humans doesn't map one-to-one on reinforcement learning algorithms or reinforcement learning brain processes. We need to understand instead that there's lots of different processes that are important for this flexible learning. And that gets me to my second part, which is whether those different processes are indeed bugs that just happen because evolution is messy and gets us, to having flexible behavior, whichever way it gets there, or whether they are indeed features that then should be considered as important for anyone trying to develop artificial intelligence in artificial agents. And so before I go to this part, I'm happy to pause and answer any questions. Please let me know if there's any questions.
Oh, okay, someone wants to ask a question.
Okay. Sorry, did you say there was a question or there wasn't?
Yes, someone is opening his mic.
Hi, can you hear me?
Yes.
Yeah, hi. Yeah, considering like all these kinds of like learning process, if there is any like evidence about the like arbitrating between them, like in different tasks, maybe people will rely on different kind of like a learning process. Maybe in some tasks, then rely on like more working memory. Sometimes then rely on like habitual learning. I'm not sure if there is something like evidence about this arbitration.
Yeah. So you're asking about the meta process of selecting a different process.
Exactly.
Yeah.
Yeah.
So people try to study this, and there is evidence that people, to some degree, adjust their weighting of different processes. Um, but to be honest, I think that we don't quite understand well enough yet what the processes are really. Um, and so we have good evidence that you don't behave exactly under different task statistics. So for example, that if the reward statistics change all the time, for example, you're going to be less likely to depend on habitual kind of processes. um, but we're not even sure about that, and partly it's because it's really hard to measure what those processes are. You see that in my task, we had to do quite a bit of work to actually isolate working memory there, for example. And so it's been a huge challenge for our community to even identify what those processes are. We're still working on it. And so even though we have evidence that people behave differently, we have a hard time pinning it down because we haven't with high confidence identified those processes well yet.
I see. I'm not sure if we can uh, do this process through like comparison of like modeling parameters across different tasks. Like we feed the same kind of model and we extract the parameters for different learning process and we compare them across different tasks. I'm not sure if we can do this.
Yeah, so you can do this, and we've done this, and we've shown actually how poorly comparable the parameters are across different tasks. The problem with doing this is that let me show you something. So you see here, these learning curves here. There in the end, I showed that the working memory with habit worked better than the working memory with reinforcement learning. But really they're very similar, right? Like I really
Yeah,
had to do this error analysis to show that it was the habit process rather than the RL process. And for that reason, if you use the same algorithm in different tasks, you're never completely sure. It's hard to be sure essentially that you're not misattributing variance to a different parameter, right? So I was able to use an RL algorithm and do kind of an okay job, and then use the RL parameters to compare to another task. But actually, I think I was not quite attributing variance well, and so it's really fraught to do that, because essentially you might be using an RL algorithm in one task and not knowing that this RL algorithm is capturing working memory processes instead.
I
Do you see
see.
what I mean? And
Yeah,
so we think a lot of this is happening essentially in the field of using an algorithm that does a good enough job of capturing the behavior, but does not necessarily relate to the actual underlying processes.
I see. And how about we like through some like a behavioral prediction to distinguish different learning process, like in the two-stage task, we maybe use them to like distinguish the model-based and model-free. I'm not sure if there are some like a behavioral signature for the distinction between this process. Like
Yeah,
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 yeah. So the model-based, model-free two-step task is a very good example of us actually not capturing the right processes there.
oh,
Um,
really,
yeah, and I know it's been very popular and very, but I think the consensus of the field now is that it's very elegant, it's very neat, it shows very real behavioral differences,
yeah,
um, but we really don't think they actually end up mapping onto the right processes underneath it. So, for example, I think the more free side of it is probably capturing both some working memory and some habit processes, and the model-based side is definitely dependent on working memory, but it's not clear at all that it's using this kind of prospective, forward-looking, planning-like process as opposed to more inference-like processes, for example. So you can and you should do this kind of predictions, and this is what this is too, right? By saying like, well, the key prediction here is the set size effect, and we can see it. But it's more complex than it looks, and I think that the two-step task has been a good education to the field in that sense. It's like it looked really cool at first, and then little by little we discovered everything that was wrong about drawing too strong conclusions from it.
that makes sense. Thanks.
Thank you for the questions. Any other questions, or should I move on?
I can't see any other question.
Great, thank you. Okay, so we have those multiple processes, and I want to stress that by no means do I mean this to be a final or complete or description of what those processes are. I think it's definitely more complex, but it's already complex enough. And so this question of, okay, why do we have this complex architecture to just support um, flexible learning, and what are those bugs or are those features? So I'm going to talk about a few concepts in there, and I'm going to then walk through them a little bit, trying to think for each of them whether they're bugs or features. Okay. So there's a feature of a process that it's simplicity. And simplicity, for example, the habit algorithm is the simplest of all because it's just strengthening whatever happened. And we can ask whether that's a bug or feature. Redundancy. We have multiple processes that could all do the task on their own. Why are we trying to use all of them? Trade-offs. We have different processes that can do the task but do them slightly differently. We have very strong bottlenecks in some of those processes. So, for example, working memory has a very strong information limitation, and that very much looks like a bug often, but I think maybe it's a feature. And I'll talk about complexity too. Okay, so let's start with simplicity, and let's take this habit mechanism. So this habit mechanism is about as dumb as you can think. A learning mechanism. It's just strengthening whichever action you're doing, irrespective of the outcome. Okay, so this process is obviously suboptimal for learning. It doesn't track value; it tracks frequency or co-occurrence, and it says that making an error makes it more likely rather than less. So it does not seem like a helpful algorithm at all. And sorry. To show that you can just simulate it, right? You can simulate it in a more complex task than what I did. So, for example, probabilistic task where you need to learn to pick between A and B, and A gives you reward 1 with probability P and 0 otherwise, and B is the reverse one. Okay, and you can simulate it and see what policy it develops, and ignore this line, for example, at first. Like, just look at this blue line here. What you'll see is that the policy, as a function of the probability that R gives you 1 here, is completely random. It's at 0.5, right? And that's logical, right? Because it just tends to repeat whatever it did irrespective of outcome, so it shouldn't be sensitive at all to the probability. But if you assume that the policy is a mixture policy, not just the policy of this habit agent, but also is guided by a working memory process that is sensitive to outcomes, then the habit module does learn a policy. And the idea is, again, very simple. It's that if you have a little bit of information about which action is good, that is going to bootstrap your choices. And so that is going to make you pick action A more than action B sufficiently frequently that H is going to learn to iterate on the good action, which is going to let it create a good policy. And this policy looks exactly like an error policy. So that's interesting, because if you have a little bit of a good policy, then this super simple process is learning as good a policy as an error algorithm with much simpler computation. So this could be thought of as a bug because it's not a process that learns on its own, but it could be thought of as a feature because we're able to essentially distill a good policy out of very little information out of other processes. And so maybe that's a useful principle. So of course that gets us to redundancy. This is only feasible if you have another processes that's redundant. So we can think of There's redundancy here, which is having working memory and habit, both doing the task or RL. And this partial redundancy in working memory and habits kind of mitigates each other's limitations. So habit just can't learn a good policy, and working memory can, but only for a very small amount of information. But together they end up being able to build a really strong policy. So then you might ask why you have the trade-offs. Like, why couldn't you just have a working memory process that just has high capacity and isn't forgetful? And why can't you have just the best of both worlds? So here what we think of is that when you have there's going to be an information trade-off, essentially. So the fact that working memory can learn quickly versus RL, which is slow, is going to also be helpful. And by the way, we really think this RL or this habit process is very slow. So for example, we did an experiment here where we had participants learn just one bit of information every day, once a day, rather than in a continuous experiment, to see how quickly they would learn. If you look at the red curve here, it's the same experiment as before, but with just one trial a day. And you see that it takes, by 24 days here in this red curve, participants are still only at about 0.5 accuracy, started from chains at about 0.5 accuracy. They're very slow. It's going to take like something like 25 rewards up to 100 iterations to learn something if you can't use working memory at all. So why is it not faster? Why is this like slow process so slow? And why is the working memory process that's very fast so limited? So fast working memory allows fast learning, which is essential when things change fast. And that gets a little bit at the question we were discussing earlier. But that could also mean catastrophic forgetting, in a sense. That could also mean that if you're learning new associations very quickly, you're erasing past associations very quickly too. By contrast, the slow reinforcement learning process might allow robust long-term learning, which might be really essential in stable environments, but of course is really bad in this type of experiment. Where all the information is available from the start. And that's something we can show too in experiments. So we did the same experiment as I showed you earlier, where participants learned stimulus action association very quickly. And they did that for 20 blocks for like really 45 minutes or so. Then they did something else for 5 minutes. And then we asked them to remember everything they had learned without giving them feedback. Okay, so they had something like 85 stimulus action associations, a huge amount of information. And we just told them randomly mixed up all the stimuli and asked them to pick the correct action for each one. Okay, so pretty hard. And we weren't sure how well people would do. But we were sure that in this case, they couldn't use working memory at all. Okay, so we could only see RL or habit processes there. And so when we do that, the learning looks like before, and we only have set size 3 and 6 here. We have a strong effect of set size, which means people are really using working memory in set size 3. And you can just plot it this way by showing their overall accuracy in set size 3 and 6, and the difference is positive. But then when we looked at the test phase accuracy after they had learned, we showed the opposite effect. And we showed that people were better at the harder condition. They they remembered better what they had learned under set size 6 compared to set size 3. And we think that this is exactly showing those trade-offs, is that because you've learned really fast in set size 3, you've kind of blocked your slower learning process, and you are just not remembering as well. You're not building as strong associations. Okay, so having this trade-off ends up being really essential to being able to adapt to either short-term or fast-term or long-term learning. So again, we think this is a really important feature of human flexible learning, that it has multiple sources of information that specialize in different ends of a trade-off, that allows us hopefully to weigh those different processes different in different environments, to optimize their learning. And again, going back to the question that we had earlier. So another trade-off that we have is this low working memory capacity, and that's been really puzzling. Why we have such low capacity? Working memory is such a flexible resource, very able to store any type of information very accurately, and it's very puzzling why it's so low, this capacity of this resource. When we measure working memory in this task, we find roughly 3 bits of information. This is in adults, this is in patients, this is in kids, teenagers, adults. You see, like we end up at roughly 3, for no matter what population we get, and that's very consistent with the rest of the working memory literature. So why not more? Is that a bug or a feature? And people doing AI typically think it's a bug, and typically think that if they get an RNN that is a bit working memory like, and give it more capacity, it's always going to be better, and that somehow this is a limitation of our brain. Maybe that it's hard to design a neural network that will hold more information, and that our evolution just hasn't gotten there, essentially. And it's true that this is difficult in many ways, but I think we should very much consider the alternative interpretation, that this isn't the case, and that it's not true that this is a bug, and that for that reason this is irrelevant to AI. And the reason I don't think so, I think it's actually a feature, is that I think this low capacity forces an information bottleneck. So it's a little bit like attention, which of course is very famous these days, that it forces an information bottleneck that forces us essentially to represent only the key information and focus on it so that we can learn fast on this. Okay, so if you think about it, when you're learning to process a scene, it's super highly dimensional, and that's going to make learning very slow because of the curse of dimensionality. But if you force dimensionality reduction through a low capacity, you might be able to focus on a smaller state space that only has the key information, here the fact that the light is red, which then will allow you to plan or to make decisions much more efficiently. And for example, this paper here showed this in simulations. Also having lower dimensionality forces you to do some clustering, some generalization, so some clustering of the state space that should enable generalization in ways that we've also shown occurs in humans. Importantly, so then that would be relevant to artificial intelligence, and thinking about working memory as a capacity-limited process might be really important to modeling fast behavior. Something that's important also, I think, is that generalization is not always linked to dimensionality reduction. So we think a lot about dimensionality reduction for creating smaller state spaces, faster processing, etc. But there's also strong evidence that humans over-complexify things sometimes. So create representations of problems that are more complex than needed. So this is an example that you might be familiar with, of me drawing randomly dots in this square, and on the left it's drawn randomly, and on the right it's drawn pseudo randomly. I've forced some structure on the right, but the right one seems much more. Most humans will perceive the right one as more random than the left one that is perceived as more cluttered, and that's not true. And that's because we look for structure in the in our environment. So that's been shown, for example, really well in this paper by Angela Yu and colleagues that shows that people are much faster at answering, at reacting to patterns that are um, that have regularity. So, for example, something that repeats all the time, like this RRR or AAAA, participants will react much faster to it than to something that is irregular, like this AAAR pattern here. And this was an experiment where participants just pressed left or right when they were told left or right. So no learning, but people just learned the statistics of the task and just assume that there was structure where there wasn't. Okay, so people are known to create this type of complexification, and it seems again to be a bug. But when you create this type of complexification, then sometimes you find you have the space for creating structure that will then allow you to generalize in new environments. And that's what we showed in our reinforcement learning experiment, but I'm going to skip that for the sake of time. I'm happy to answer questions later. Okay, so we think that complexity, strong structural representations that might look like a bug, like trying to find patterns where there are no patterns, is actually also probably a feature that creates inductive biases that enable transfer and generalization, which is crucial for fast learning. And that may be resource optimal when we work on low dimensional states by creating divide and conquer approaches. And there is actually some evidence of this type of benefits in AI out there. So to conclude, I think that humans work with really high dimensional complex input, and they have all kind of process aspects that might look like bugs, but that actually are features that allow them to be as efficient as they are. So for example, having a bottleneck in working memory will allow them to create a small state space. Having a bias to look for complexity in the environment will give them a bias, an inductive bias that there is structure in the environment that will let them create that structure and give them a capacity for generalization, which then will lead to fast and flexible learning. But because they also have redundant processes that process things differently, for example, with slow and efficient and a very simple robust learning, this in parallel will be able to distill those more complex policies and lead to robust policies where things are stable. Okay, so I hope the goal was to look at human learning and try to understand cognition and the computation supporting human intelligence and think of them as whether they're bugs or features. The study of human learning benefits a lot from input from AI, but I think that the reverse is true too, that we can look at the processes in humans and maybe bring back some of those ideas to AI. So thank you so much for your attention and all my funding and collaborators, and I'm happy to take questions. Sorry.
Thank you for your great presentation, Professor. No, we're open to question. If you want to ask question, please raise your hand and I'll give you access.
Hey, Professor. Thanks for your great talk. I wanted to ask about habits.
Yeah.
Like you mentioned, like about the algorithms of the habits, which seems pretty simple. But I wanted to ask why is so hard to like create habits in humans? Like I mean, like why like these associations between neurons is so difficult, while the habit itself, it has a very simple structure. Like we have to just repeat the things until it's the association is happening in our brain, but yet it is so difficult to create a habit or change a habit. Like if you have a bad habit, change it to a good one.
Yeah, so the last question is easy, right? If you have a bad habit, change it to a good one. That's hard because you've created a very robust association, and that's exerting itself, and unlearning it is going to be difficult. Learning it is difficult too, because I think as I showed, when you take away other processes, let me find the right slide. Um, when you take away other processes, um, learning is incredibly slow. Okay, so this is learning stimulus association, where you try each stimulus just once a day, and this is by trial 24. The different lines are slightly different conditions. You can ignore it, but by the 24-day, it's still very slow. So there is, something slow about the biology of this, which is probably really physical, creating synapses, reinforcing them. That is slow in the absence of the other processes. And that tells us that most of our other learning is not this process, is those other processes that are very fast but very fleeting. Um, and as humans, we have those trade-offs, right? Like, and we drive most of our behavior, well, not most, but at least when we are trying to go for a goal, um, we are going to engage our goal-directed processes, which are dependent on executive function and working memory, and which are going to override, to some degree, those habits. And if whatever your choices are not consistent with those habits, it's going to take as long as you've experienced enough of those stimulus action iterations to build it, to create the habit. So I think seen in that lens, that's why it's hard. But it's a very good question, and it's a question that's been hard to study, because it takes time to learn habits, and because participants in the lab tend to be in a state where they try hard, and so they don't let their habits be expressed. And so it's something we've been studying actually in my lab, and trying to see, like, okay, how can we get people to actually let go, and stop paying so much attention, and actually, let the habits be expressed. But it's a very important question, and a very difficult one. And I don't have a perfect answer. Sorry.
I see. I see. And like for those that you have experiments in the lab, like, do you find any like associations that help them to generate habits more easily? Like, do you have any advice for like people to generate habits?
Yeah, I mean, there's a whole literature on this that is more from the real life kind of setup, and the advice is essentially to have very consistent stimulus action associations, right? So um, um, habits are typically cued, right? And there's going to be a very specific state that you're in that triggers that habit. And so if you want to build habits, typically people advise that you uh, try to build it in a very consistent way. So rather, if you're trying to, not forget to brush teeth or something like that, to tie that to something that happens very regularly, essentially. So do it right after dinner, right? So that it becomes like tied to something that happens all the time. Or if you want to exercise, like have some kind of visual cue, like have your gym bag right in front of your nose in the morning, so that you see it, you grab it, you exercise. The consistency of the stimulus action association is an advice that people have been giving. The thing that's more relevant to my own research is that we have those other processes that might or might not be in agreement with, developing those habits. And if they're not in agreement, they're going to be very strong at overriding the habits until it's built. And so that means that you need to somehow avoid those other processes, meaning avoiding any friction that will give you an excuse to say, like, actually, I want to go, prep for my exam instead of exercising or something like that. It's a very good argument, right? But if it's not consistent with your habit building, and we're very good at using those other goal-directed processes to guide our direction or our choices, which then might impact the building of habits.
I see. Thank you
Yeah.
very much.
You're welcome. Thank you for the question.
Oh, hi. Thanks
Oh,
for.
hi.
Yeah, I have another question. Yeah, regarding the topic flexible learning, I guess we have something, a huge part we haven't been covered today. That is how we incorporate those like semantic knowledge to facilitate learning. Take the example you gave before. If we find the apple smells good, we might assume it has better quality, thus higher value. And
Yeah.
I'm really curious about like what might be the and the algorithm level, what might be the formal process or like models like to facilitate this kind of integration process. I'm not sure if there is any like existing work on this.
Yeah, I mean, a little bit, but at least I don't do much of this. But essentially, you can think that we have this whole store of knowledge that we can tap on through episodic memory or semantic memory. And I think what happens is essentially you tap into this and then create a policy in working memory. So essentially, in my experiments, I assume working memory is blank and you're just getting information and filling it in. But in
Yeah.
real life, most likely you can extract information from your broad base of knowledge, transform it into a policy, which is kind of amazing, right? Like compared to
Yeah.
non-human animals, and then hold that working memory policy and work from there. So I think it's still very relevant. This working memory. It's just that where the information is coming from might be different in that sense.
I see. In that sense, we might say like our working memory is a kind of like a like online extraction of this kind of knowledge.
Yeah, sure, absolutely. Yeah. It's kind of interesting. The reason working memory is poorly studied in the context of learning, I think, is that it's really not a learning process per se, right? It's
Yeah.
by definition it forgets very quickly, and so it's hard to think about it as a learning process, but it supports learning by directing, but by being really essential in making choices using short-term information. And so to me that means that it is really a learning process, even though it's only scaffolding in many ways the rest of the learning.
I see. This sounds more like information operation process. Yeah.
Sure, you can call it that if you want. Yeah.
I'm really curious about like how can we incorporate like the descriptive information and some like experiential information. Yeah, I'm not sure if there is like some models we like talk about this.
So you mean you're seeing someone else do the learn and see what you get out of it?
Like by description, I mean like a rule or like expression of the
Oh,
policy. Yeah, versus like experiential is that I learn it through my own experience. And I'm
yeah.
curious about how can these two formats of like policies integrate together, and what might be the computation process allow
It's
this?
very executive and prefrontal. There's a field that's called rapid instructed task learning, or RITL, RITL. That is pretty fascinating, right? Because
Yeah,
it is one of the main differences with humans, right? Like thanks to language, like we can tell participants, like if you see, a triangle, press left. If you see a square, press right, and off you
yeah,
go. You're good. And of course, you can't do that with monkeys, right? And uh, but the thing is, so this field tries to study this and shows the importance of prefrontal processes in this. Um, and it's very interesting in the sense that it's rapid, but it's not immediate. Um, and they've shown that essentially there's this 2-3 trial kind of period that's crucial after you've encoded a role, where the rule is present and you can apply it, but it hasn't quite settled. And we don't know much more than that, how it works and what's happening. Or at least I don't know much more than that. Last I looked, it was a few years ago, but it's pretty mysterious. I mean, clearly it's getting into some form of policy that is able to mix with more learned policies.
Yeah.
Um, through prefrontal, subcortical loops, which also serve for the longer term uh, kind of processes that are sometimes more cortical, but we don't know really. Yeah.
See, yeah, that's a good topic. Thanks.
Thank you.
Thank you, Professor. I have a question about habits too. My question is about what is the relationship between habitual learning and value learning? Because I see when we want to do something frequently, there's an implicit value function involved that causes us to do it. Either we have this value function or it is enforced by us by the environment that we're in. My question is, what is the relationship between value learning and habitual learning?
Yeah, no, that's an interesting question, right? Like there's the whole, reward is everything kind of approach to this. Um, I think, I mean, it's a complex question, but I think if we set aside the AI side of it and think more from the human side of it, um, in the end, whenever you're making a choice, somehow we can say there's an implicit value function, but we can ask like, where is it coming from? Like, where and is it meaningful at all? Right? And in this case, where I'm showing the error patterns here. Where is it? In the end, what's striking is that this process is just more likely to repeat an error, right? And so it is just insensitive to external rewards, right? And so you can translate this to saying like, well, okay, my reward function here is that whatever I do is rewarded, right? That's just not very informative, right? And it's just not leading you to um, any good policy, right? And so yes, you could rewrite this as being value learning with the appropriate value function, but then you'd have to assume that people have those very different value functions operating in parallel for different processes, and that some of them are really stupid. And so it's one of those slightly philosophical points, I think, that's like, I can see the point that I could reinterpret this as reinforcement learning with appropriate value function, but I think I would have lost all the essence of reinforcement learning in doing so, essentially. And so that it's maybe useful in terms of thinking about algorithms, and how they might lead us there, but it's not useful in terms of explaining what the processes are and especially what the brain is doing with them.
Okay,
Yeah,
okay. Thank you,
yeah.
thank you. I need to think more about it. But thank you, thank you.
Yeah.
Let's see if other people have question. If not, can I ask you even a broad question about AI and okay. My question is, what do you think about the way that we are building intelligent system right now? That we build giant prediction machines with all the human knowledge and do a little bit of reinforcement learning on top of it, and then try to make agentic system with different experts of them, and we get good results with them. But my question is, from the way that you understand the natural intelligence and the and cognitive science, how do you see this approach? When do you see this? Do you see it would plateau in the future? Do you see there's some parts that missing in the way that the natural intelligence work in it? And uh, where do you think we have to look to see uh, what's missing to build a real intelligence. If you want to go beyond our intelligence, make a super intelligence maybe someday.
Yeah, I mean that's the big question, right?
Yeah.
um, I'm not sure, but I think structure. I think I could put a small bet on any of those all those things I listed at the end. Essentially, I think I think structure is important. I think bottlenecks are important. Uh, I, I think redundancy is important, but in ways that are different from all of those processes are present to some degree, right? In modern agents. Um, but in ways that are very, I don't know, distributed and half-hearted to some degree. And I think if we build uh, my vague intuition, and I'm completely intuiting here, is that if we put a bit more explicit structure on like actively trying to force the different processes at different ends of I'm going to be good at like big stats, I'm going to be good at like attention, I'm going to be good at um extrapolating, like being more complex at the cost of sometimes making stuff up, but sometimes being able to generalize things, and then put those together, the way we have processes that do very different things but then come together to do good things, might be good. But in the end, I actually think the better answer is all of this we do so much more efficiently, right? And so I think in the end, the way we cognitive scientists identify those processes is by showing where they fail, right? Like by showing like, oh, we're doing so well except in this one silly little thing, like see how wrong it is. And typically those wrong things um are really robust good case examples, but very not relevant to everyday life, right? Like those errors I'm showing you, it's like that's super robust finding. I actually replicated it 6 times. But those are the errors, right? And in the end we want people to make the good choices, so whatever, right? But that's so informative, right? Because I think it shows us like we've built a very close to optimal but not optimal process, and the way we've done that is by accepting those small errors for this increased gain in efficiency, right? Like, okay, this habit process is really stupidly simple and it can't do anything well on its own, but it's so much more simple, and in the end it gets us a pretty good policy with just that little bug in it, right? And I think if we could somehow get back to this idea of like we don't need optimal, actually we need close to optimal and much more efficient, might be a good way forward. Yeah, I don't
So,
know.
so, so and again, no, that's great. Thanks for sharing your intuition with us. So you think for going and focusing on being efficient with building this system could give us insights into how natural intelligence works?
I think so,
Maybe.
yeah.
Okay.
Yeah, yeah, yeah,
Uh,
yeah, I
and
think so.
and do you think there's any big idea that we're missing that is here, but we're not trying to engineer it properly?
um I don't know, I don't know what people are trying right now. Like, there's so much work, right? Trying to I don't know how anyone follows the pace of AI these days, but um I don't think any of the ideas I talked about at the end are new ideas. I think like most likely someone is working on some of them right now. um maybe people are not taking the working memory kind of limitation as a feature idea quite strongly enough. Um but I think in the end it's going to be the combination, right? I think people tend to have a bias for elegance, or like unification or stuff like that, and I think in the end the brain is highly messy and it's the messiness of like having lots of different things approximately correct, that ends up making a very robust and flexible system. And so I think stepping away a little bit from like, elegant single system solutions to more like, it's going to take some hacking, like, might also be my inelegant answer.
Okay, okay, thank you for trying to answer this question. I know it's very, very messy to try even to answer it, but thank you
Yeah.
for it. Yeah. And if I don't know if other audience have question, but if there is no question, I can ask a closing question. Okay. My closing question is, what's your general advice for the new researchers, new students that wants to start their research career and wants to go and find some interesting question that wants to work on, or trying to find out what they're passionate about and how do they go about their research journey. I want you to give them some advice for the.
Yeah. Um, I think you have to be mindful of short-term and long-term goals, and I think you need a healthy balance between them. And it's going to be somewhat field dependent, obviously, but I think there's lots of low-hanging fruits in many fields, and it's good to pick some of those because it's good for your career. Um, but then the less low-hanging fruit might be higher reward in the end, and they might build your career better long term. Like to actually discover something really interesting and new. um, yeah, you need papers on your CV, and then you need also to be the creator of big new ideas, and finding the right balance between those is very difficult, really, I think. And but you can't do it if you're not aware of that tension. And so being aware and then thinking hard about that tension and where you want to put yourself, I think might be very important.
How we can be aware of that? Is there some practice that we have to do? No.
I typically tell my students to have an easy project and a hard project.
Okay.
Yeah, I mean, but again, that's going to be super field dependent, right? There's fields where you can't do that, and there's fields where you can have 15 projects at the same time. So, but in my case, like I tried to have a clear plan of like, okay, this paper, is not going to be a nature or science paper, but it's going to be a paper, and it's going to be fine. And this idea, might fail spectacularly or might be like a big paper. And that's the risky one, and it's going to take longer. And we can, we can take that risk if we have a backup, essentially. Yeah.
Okay. Thank you for your great advice. I think with that, we can finish the session. And thank you again for accepting our invitation. We are
Yeah.
truly honored today to have you with us, and we learn a lot from you. Thank you.
Thank you.
Thank you. Have a
Bye.
good rest of the day.
Thank you. How do I turn off?
On the top right, there's a camera button and there's the microphone.
Oh, yeah. Bye.
Goodbye.